Now let's move on to section 4 of this notebook, limit and convergence. This is an optional topic. In fact, this topic is so advanced that even the top level Calc 2 students will have difficulty following. Of course, I'm not going to write any exam problem or anything like that here, and you'll be able to come up with an A in this course without studying any of it. Now, in that case, one may ask, what's the point? Well, here is my response. This is according to my long-term strategic plan for mathematics major. This topic, limit and convergence, happens to be the single most important topic in entire mathematics major program. And you cannot get away from this if you're a mathematics major, minor, or IS major with 4th through 8th grade math teacher preparation program. Which means almost everybody who's taking this course here will have to do this one way or other. And this topic is rather challenging to get through in a single course. I mean, Math 3000 Real Analysis 1 is supposed to be that course. However, it's going to be very challenging to acquire a certain level of proficiency and mastery through just a single course, Math 3000. As a matter of fact, most of the textbooks that cover Math 3000, including the one we are using, the Lay's analysis book, assumes some kind of acquaintance on limit and convergence and continuity beforehand. I'm not trying to accomplish some proficiency here, some acquaintance. That's my purpose here. And our textbook by James Stewart begins that process in Calculus 1 level. In Chapter 2, if I remember correctly, 2.4 or 2.5, our textbook author already starts it. And that's for acquaintance purpose, some exposure. I delayed it for 1 semester, and we are studying it now in Calc 2. And then my strategic plan is to reinforce it twice again in Math 2000, discrete mathematics, and then Math 2730, multivariable calculus, before reaching Math 3000, real analysis 1. And of course, after real analysis 1, with all those prior exposure, you'll be able to succeed much better. And then afterward, you may go through with Math 3610, real analysis 2, and get really ready to engage some applications of calculus in, well, all kind of places. For example, if you go over to a lot of STEM industries, application of calculus is everywhere, which means this topic, limit and convergence, will lead to much wider career options for you. And that's why I'm trying to cover it here in Calculus 2 to a certain degree, even though this topic is not directly tied to exam problems or grades for this particular course. Okay, enough digression. And I hope you understood me about the importance of this topic. Let's move on. Here we go. We define the limit of sequence as follows. Let's say an is a real sequence, and we say an approaches to a, or an converges to a as n goes to infinity if the following condition holds. And then we see something terrifying. It kind of reads like this. For any positive real number epsilon, there exists a certain natural number capital N which depends upon epsilon, such that whenever small n is greater than a capital N, the distance between an and a is less than epsilon, the first positive real number selected. And we can decompose that meaning into following. We can roughly translate like this. The distance between an and a gets arbitrarily small as natural number small n gets sufficiently large. And what do you mean by arbitrarily small and sufficiently large? We have color coding here. What do you mean by arbitrarily small? And this quantity is less than arbitrarily small real number. So we have to select an arbitrarily small positive real number, and the quantity we are looking for, the distance between an and a, has to be less than that arbitrarily small positive real number. Now, what do you mean by sufficiently large? The small n has to be larger than a certain bound, capital N, which is a natural number. And the bound for that arbitrarily small positive number, of course, was 0. Likewise, we have to have a bound for n, small n, and that bound is capital N. And of course, we are dealing with sequences, so all the indices are natural numbers, so that capital N has to be a natural number. So sufficiently large means there exists a certain bound, and arbitrarily small means everything, arbitrarily selected epsilon. Now, there are some students who get confused by this term arbitrarily small, as if you can select arbitrarily. No, that's not what it means. It's not you who is selecting it arbitrarily, and you can simply select epsilon as a big number and then just make everybody happy. But then again, that's not really arbitrary, because the person who selects is just you, not arbitrary person. So arbitrarily small means the selection is done by arbitrary person as well. That includes your mean instructor, like me, and I'm going to give you a really, really small epsilon and then take that. Somehow you have to come up with a capital N value. Even that works out. Let's see. Let's go over to an example. I prepared a couple of examples here. And let's begin with 4.2, this example. And this kind of helps you understand what is meant by sufficiently large part. So if you go over to this color coding, this color coding here, and then compare that with this example 4.2, the sufficiently large part, the middle part is all gone. In other words, we just want to find out a sequence an so that the distance between a and a is arbitrarily small, period. No condition about n getting sufficiently large. In that case, what? Well, an minus a has to be arbitrarily small. It has to be less than arbitrary positive number. And what kind of number is less than arbitrary positive number? No positive number is less than itself, less than half of itself, which means if a number is less than every positive real number, it cannot be positive. It has to be non-positive real number. In other words, an minus a has to be less than or equal to 0. Otherwise, we have a contradiction, because an minus a in absolute value itself is a positive number, and no number is less than itself. Okay, so this absolute value is less than or equal to 0, and the absolute value is always greater than or equal to 0. So what do we have? Absolute value has to be equal to 0, and consequently an has to be equal to a. That's what we get. So if we throw away the middle condition, sufficiently large part, then all we get is a constant sequence. And limit is actually a little bit relaxed than constant sequence. Constant is even more stringent. So stringent it is not interesting. Now, how about the middle part, the all-important middle part? Let's go over to a couple of examples how to deal with those. In some very special, simple cases, we can actually find out this capital N, which must depend upon epsilon, in explicit terms or semi-explicit terms, kind of like this. Let's go to the first example here. Prove that the limit is 0 when an is 1 over n squared. So we have to prove this one. For arbitrary epsilon, we can find out certain capital N, which depends upon epsilon. We will have to explicitly find it, so that the difference is less than epsilon. So let's begin with selecting arbitrary epsilon. Let's select arbitrary epsilon. And then the key part is selecting capital N. All we have to do is to select a certain capital N that is greater than 1 over square root of epsilon in this particular case. Why 1 over square root of epsilon? Well, it'll turn out necessary in the end. And of course, we cannot select N as equal to 1 over square root of epsilon because that number is not a natural number. So we'd better select a natural number greater than that. Is it always possible? Actually, there is very, very difficult theorem hidden behind it called Archimedean property, Archimedean theorem, but let's skip that. That belongs to 3610. Okay, so let's select capital N greater than 1 over square root of epsilon. Okay, we selected it. And then let's consider small n greater than that capital N. In that case, what? The distance between A and A is actually nothing more than 1 over n squared minus 0, because A is 0 and an is 1 over n squared. Well, minus 0 doesn't change anything, and 1 over n squared is always positive, so we can throw away the absolute value and we get just 1 over n squared. And let's make this observation. Whenever n is greater than the capital N, 1 over n has to be less than that 1 over capital N. If you square it, the same deal. So because n is greater than capital N, 1 over n squared is less than 1 over capital N squared, and that is less than 1 over square root of epsilon squared. Eventually, we have less than epsilon. So that's how we can explicitly prove that this sequence has limit 0. This was an exceptional case where we could actually find out capital N as explicit expression of an epsilon. The next problem is slightly more complicated, but again simply enough that we can find out capital N as an explicit expression of an epsilon. And here we go. For arbitrary given epsilon, we just select capital N as a natural number greater than square root of 2 over epsilon minus 1. And that's going to be a positive number because epsilon is going to be really small. And then, of course, we can find out any capital N greater than that. Okay, we do that. And then this difference of Bn and B, or this n squared minus 1 over n squared plus 1 minus 1, that can be calculated and algebraically manipulated as follows. Subtraction, and then we take the common denominator, and then we have, let's see, this n squared and n squared will cancel out. We have negative 2n over 1 over that. So we'll have something like this. But denominator is always positive, and negative 2 we can always flip it to positive to bring it outside the absolute value. So we have that. And then we do the same thing when n is greater than capital N, because capital N and the n are in denominator, we have the other direction of inequality, 2 over capital N squared. And what is 2 over capital N squared? Well, n is greater than the square root, so put it in there, and then algebraically manipulate it. It turns out that 2 over that square root squared plus 1 is just epsilon. And as a matter of fact, that's why we selected this one as our bound capital N to begin with. In the end, we have this quantity, Bn minus Bn absolute value is less than epsilon. It's arbitrarily small, we found out.